Hi guys, in this video we are going to learn about the some topics which is related to the electrochemistry. It is a Kohlrausch law, applications of Kohlrausch law, conductometric titrations for acid and bases. See here, what is the Kohlrausch law? Kohlrausch formulated a law in 1875 and after his name it is stated as the Kohlrausch law. Then what is the Kohlrausch law? That is the equivalent conductance at infinite dilution for any electrolyte is the sum of the equivalent conductance for the cation anion at infinite dilution. Means here in this case, if we want to determine the equivalent conductance of a sodium chloride, then the equivalent conductance of the electrolytic solution of the sodium chloride, it is nothing but it is the sum of the equivalent conductance of sodium ion as well as the chloride ion at infinite dilution. And mathematically, the Kohlrausch law can be stated as the equivalent conductance at infinite dilution for a particular electrolyte, it is equal to, that is a sum of the equivalent conductances of the cation and anion at infinite dilution. Means lambda infinity, it is equal to lambda equivalent conductance of cation, that lambda infinity of the cation plus lambda infinity of the anion. Lambda infinity of the cation and lambda infinity of anion in this case means lambda infinity of positive charge and lambda negative are the equivalent conductance of the cations and anions respectively at infinite dilution. This law is to be also be valid for the molar conductance at infinite dilution. And then what are the applications of Kohlrausch law? The Kohlrausch law is applied to calculate the equivalent conductance at infinite dilution for weak electrolytes. It is also be used to determine the degree of dissociation of weak electrolytes, ionic product of water, absolute ionic mobility, and the solubility product of sparingly soluble salts. Then firstly we will see about how the Kohlrausch law is used to determine the equivalent conductance or the molar conductance for weak electrolyte at infinite dilution. Here in this case, the equivalent conductance at infinite dilution for strong electrolyte can be calculated using the graphical method, but the graphical method is not applied to the weak electrolytes as they are very slightly ionized. But Kohlrausch law can be used to determine the equivalent conductance at infinite dilution for a weak electrolyte. Suppose if we have taken the you have to consider the determination of equivalent conductance of weak acetic acid. When this acetic acid is treated with the sodium chloride, then it forms a corresponding sodium acetate and hydrochloric acid. To determine the equivalent conductance of this acetic acid at infinite dilution or the molar conductance at an infinite dilution, because this Kohlrausch law, it is to be applied to calculate the equivalent conductance as well as the molar conductance at infinite dilution. Suppose here in this case we want to determine the molar conductance of the weak acetic acid at infinite dilution, then from the values of the molar conductance of hydrochloric acid, molar conductance of sodium acetate and the molar conductance of sodium chloride, we can determine the molar conductance of the acetic acid at infinite dilution. See here, that is a molar conductance of, or the equation for determining the molar conductance of the acetic acid can be written as, that is lambda infinity for acetic acid, it is equal to the lambda infinity of sodium acetate plus lambda infinity of hydrochloric acid minus lambda infinity of sodium chloride. Means to get the above equation or to calculate the molar conductance of the acetic acid at infinite dilution, we have to write a such type of an equation. This equation gives, that is the molar conductance of the acetic acid, and that is to be written as, we have to separate the equivalent conductance of sodium acetate. It is nothing but the equivalent conductance of the sum of the equivalent conductance or the molar conductance of acetate ion and the molar conductance of sodium ion. Similarly, the whatever may be the molar conductance of the hydrochloric acid, it is nothing but the, according to the Kohlrausch law, that it is the molar conductance of H plus ions and the molar conductance of the anion chloride ions minus the molar conductance of the sodium ion minus molar conductance of the chloride ions. Okay, we have to split the molar conductances of the sodium acetate, hydrochloric acid and the sodium chloride according to the Kohlrausch law. And if we know the molar conductances of the acetate ion, molar conductance of sodium ion, molar conductance of H plus ions and the molar conductance of chloride ions, then we can calculate the molar conductance of acetic acid. In the above equation, that is the molar conductance of sodium ion, it is to be cancelled with the molar conductance of this sodium ion. It has the positive sign and it has the negative sign. Similarly, that is a molar conductances of the chloride ion, and this molar conductance of this chloride ion, it gets cancelled and we will get the final equation as the molar conductance of the H plus ions at infinite dilution plus molar conductance of the acetate ion at infinite dilution, and it is nothing but the molar conductance of the acetic acid at infinite dilution or the equivalent conductance of acetic acid at infinite dilution. Here in this case, in this way, we calculate the equivalent conductance or the molar conductance of weak electrolyte at infinite dilution using the Kohlrausch law. The second application is the degree of dissociation of weak electrolyte. The degree of dissociation of weak electrolyte is calculated by using the Kohlrausch law. We know the degree of dissociation, lambda infinity, it is nothing but, alpha is nothing but, that is the number of molecules dissociated into the ions divided by the total molecules present. Means fraction of the total molecules get dissociated, it is nothing but the degree of dissociation. And that is for weak electrolyte is calculated by using the Kohlrausch. I know that in case of a weak electrolyte, the weak electrolytes are to be less dissociated into the aqueous solution, and therefore the dissociation is very less, and due to that one, this Kohlrausch law is used to calculate the degree of dissociation of weak electrolyte. Then see here, we know the number of molecules dissociated, it is directly proportional to the conductivity of the molecule. Means conductivity, it is to be related with the speed as well as the number of ions formed. And therefore, here in this case, number of molecules dissociated, it is nothing but the conductivity of that electrolytic solution. And we know that is the number of molecules dissociated into ions in the above equation, it is nothing but the molar conductivity of the electrolytic solution at a particular concentration. And therefore, the total number of molecules, that is a lambda or molar conductivity at infinite dilution. And therefore, above equation it is to be written as, that is the degree of dissociation, it is equal to, that is a number of molecules dissociated into ion, it is nothing but the what? a molar conductivity of an electrolytic solution at particular concentration, that is to be designated as lambda mc, and it is divided by the total number of molecules present. It is nothing but the molar conductivity at infinite dilution. Therefore, we have to write the degree of dissociation for weak electrolyte. It is the ratio of the molar conductivity, or in this case equivalence conductance, at a particular concentration divided by the equivalent conductance or the molar conductance at infinite dilution. The next application is to determine the ionic product of water. We know that the ionic H2O, it is to be slightly dissociated, or the water, it is slightly dissociated, and therefore the dissociation of, or the ionic product of water, it is determined by using the Kohlrausch law. Water is dissociated as H plus ion plus OH minus ions. Okay, and this H plus, according to the law of chemical equilibrium, we can write the above equation as the concentration of H plus ions and the concentration of OH minus ion divided by the concentration of water. That is equal to the what? Kc. That is nothing but the Kc is nothing but the what? Equilibrium constant. And we know water is dissociated slightly, and therefore the concentration of undissociated water may be taken as the constant. And therefore above equation is written as, that is product of the concentration of H plus ions and OH minus ions, it is equal to the constant into, that is the equilibrium constant at concentration C, and that is nothing but, that is the ionic product of water, and what we call it is the Kw. Okay, and therefore above equation, it is to be written as the ionic product of water Kw, it is nothing but the product of the concentration of H plus ions and the OH minus ions. Kw is the constant at a given temperature, that is ionic product of water is constant at a given temperature, and its value can be determined by the conductometric measurement. Okay, means whatever may be the Kw, it is at a given temperature is constant, and it is the product of the concentration of hydrogen and hydroxyl ions, and it is to be expressed in terms of moles per dm cube. It is known as the ionic product of water, and this Kw is constant at a given temperature, and its numerical value can be determined experimentally by conductometric measurement. Then next one is the absolute ionic mobility. Then we know that the absolute ionic mobility means ion conductance of a particular electrolytic solution. It depends upon the mobility of ions, and different ions has a different mobility, different speed, and therefore whatever may be the conductance, that conductance is proportional to the mobility of ions. Here in this case, we have to write this is an conductance lambda O, and that is to be proportional to the what? Mu 0, that is the mobility of, or the speed of ions, and therefore this conductance, it is equal to F into mu, where mu is equal to lambda divided by the F, and where F is nothing but the what? A Faraday's constant, and its value, it is equal to 96500 coulombs, where mu 0, it is the ionic mobility, and lambda 0 is nothing but the what? Ionic conductivity. And therefore we know this lambda 0 means ionic mobility, or the absolute ionic mobility, it is equal to lambda 0 divided by F. Means conductivity, it is determined from the Kohlrausch law, and that is proportional to the what? Its mobility, and using the Faraday's constant, we can determine the absolute mobility of ions using the Kohlrausch law. Then conductometric titrations. Here in this case, we will see the conductometric titration is used to titrate the acid base. It is used for precipitation titration. It is also be used for the complexometric titrations. Here in this case, we are going to study about the acid base titrations using the conductometer. Then what is the principle of conductometric titrations? Conductance measurements are frequently employed to find the end point of titration. The end point of titration is frequently measured, accurately measured using the conductometric titration. During the another titrations using the indicators, what happens? To determine the end point or to observe the color of the solution, change in the color of the solution, it is a manual and it is to be changes with individual person, because when we going to carry out the titrations, volumetric titrations, or we carry out the titration using the indicators, then at that time 1 or 2 drops gets excess of drops gets added to the solution, and therefore the color of the solution is not the same or the constant at every time, at each time of the what reading. Therefore these instrumental titrations are very much frequent to determine the end point of the titration. Electric conductance depends upon the number and mobility of ion, that is we know. Okay, then next one is this conductometric titrations. It is based upon the mobility of ions. We know the different ions have a different types of ion mobilities, and the faster ions it gives the more conductance, and slower ions they give the what? A less conductance in the conductometer, and therefore due to the variation in the mobility of ions, we have to determine the conductance, or it gives the different types of conductance. And when we plot a graph of titration during the conductometric method, then we will get the end point. Means during the titration, one of the ion is replaced by the other ion, and these two ions differ in the ionic mobility as well as the conductivity, with results that the conductivity varies during the titration. How equivalent point will get during the conductometric titrations? On plotting the graph between the conductance and the volume of titrant added, we will get the two straight lines, and we extend these two straight lines, then we will get the point of intersection, and this point of intersection will gives the volume of the titration added or titrant added, and from that we calculate the exact equivalence point or the end point of the titration using the conductometric method. Then types of conductometric titration. There are the different types of conductometric titration, that is acid base titration, precipitation titration, again complexometric titration, etc. one. Okay, that is the redox titration is there, complexometric titration, acid base titration, and precipitation titration. All these type of titrations are carried out using the conductometer. Okay, conductometer, what it gives? Conductometer gives the conductance of an ion which is to be present in an electrolytic solution. Now, how the conductance is to be varies during the titration? That from that variation in the conductometer, we have to plot the graph, and from that we will get the equivalence point, or the end point of a titration using the conductometer. Okay, see here firstly, here in this case, we are going to study about the acid-base titrations. The conductivity of hydrogen ion, we know, or the mobility of hydrogen ion is more compared to the hydroxyl ion. And therefore, by comparing the mobility or the conductance of hydrogen ion and hydroxyl ion, we determine the end point of titration. Means during the titration, there is a variable hydrogen ions and hydroxyl ions. Means speed of the hydroxyl ion hydrogen ion is to be different, and it gives the variable conductance, and from that we determine the end point of acid-base titration. There are the different types of acid-base titrations, that is a strong acid with strong base, strong acid with weak base. Weak base, it is titrated against the strong base, and weak acid, it is also be titrated against the weak base. Then we will see one by one the strong acid versus a strong base. Strong acid such as hydrochloric acid, when it is titrated with the strong base sodium hydroxide, then we will get the sodium chloride and water. That is simply a neutralization reaction, acid-base reaction. See, in case of a graph, initially the conductance is high. We have taken the hydrochloric acid in a beaker and added a water. Then we will make an aqueous solution of hydrochloric acid, and we will get the electrolytic solution of hydrochloric acid. And to this electrolytic solution, when we add the sodium hydroxide from the burette and we dip this electrolytic solution, conductometric cell into the electrolytic solution of hydrochloric acid, and we added the sodium hydroxide to this electrolytic solution of hydrochloric acid, 1 ml or 0.5 ml at each time. During that one, when we added 0 ml of sodium hydroxide into the electrolytic solution of hydrogen chloride, in which the conductivity cell is deep, then initially there is no sodium hydroxide in the electrolytic solution. At that time, the conductance of the electrolytic solution is very high. Okay, see here in the graph. When we added, it is due to the what? The sodium, so hydrochloric acid, it consisting of a fast moving H plus ions, and due to the high mobility of H plus ions, initially the conductivity is high. When we added the sodium hydroxide from the burette, then conductivity is slowly decreases, and this decrease in the conductivity is due to the replacement of the fast moving H plus ions by the slow moving OH minus ions, and therefore the conductivity it is to be decreases. This decrease in the conductivity continues till the equivalence point. Till the equivalence point, the conductivity it is to be decreases. At equivalence point, there is only the sodium chloride, and conductivity is low. After the equivalence point, we added the excess of sodium hydroxide into the solution. Due to the OH minus ions in the solution increases, and the conductivity is also increases, and we will get such type of two straight lines and the point of intersection of these two straight lines give the equivalence point. I means from that we can determine the volume of sodium hydroxide which is to be required to neutralize the given hydrochloric acid, and from that by using the formula that is N1V1 N2V2 we know the volume of HCl taken, we know the concentration of sodium hydroxide and the volume of the sodium hydroxide which is used to neutralize the hydrochloric acid from this graph, and finally we determine the concentration of hydrochloric acid using the conductometric titration. The next one is the weak acid and strong base. See here, the different types of graphs are obtained when we titrate at different types of acids with the different types of bases. This variation in the graph is due to the what? Speed of ions, mobility of ions. Because the conductance is variable with the mobility of ions. Suppose if we have taken the acetic acid and sodium hydroxide, acetic acid is the electrolyte, weak acid, and sodium hydroxide is a strong base, then at that time it gives the